Okay, now let's actually get started. So we're just going to trust that the numbers that you were given. Who's this?
Oh yeah, I just haven't shown up to recitation.
It's still there.
Okay. We're just going to trust that the ones that he numbered are the ones that you can't do. So we'll skip over those and I'll give you a chance to try those before next week. 1B, I think this was already, wasn't this a problem on your last exam?
C today in class, so we can do that.
You did what?
We did 1A, sorry, 1A today in class.
Oh, you did do 1A, okay. So a 4-electron reduction of a nitrile. Our reducing reagent, specifically 4-electron reduction reagent, is going to be LAH. And on a nitrile, LAH, and you have to quench LAH, water or acid, it's not wrong. Gives you an amine. Yeah.
He said at the end of class, after most people played, that there were certain problems that we don't know how to do yet.
Yeah, I circled the ones that were missing.
You're in the group chat.
So we'll skip over those so you have a chance to do them, and then we'll go over them in the review session next week. So yeah, it's 1A, 1B. Is this recording backwards?
I think it shows you it reversed because it looks unnatural. Like,
Yeah.
Did you see your face when it's not reversed?
Yeah, but then it reverses back to normal. Okay,
Yeah.
cool. 1B I think was a problem that was on your exam 1. Structural isomer of 2-butanone. That's more reactive with nucleophiles. So that's 2-butanone. That's kind of redundant. You don't really need the 2 because there's only one ketone that you can have with 4 carbons. Butanone. The isomer that's more reactive is an aldehyde. 4. And this is butanol.
Thank you.
Okay. All right, 1C, a reactant reagent product for synthesizing a ketal. Ketals come from ketones. You can have that little mnemonic. An acetal comes from an aldehyde. The A's match up, and then ketals from ketone. It doesn't specify cyclic, so I'm just going to draw a regular one. This is PTOSH, para-toluene sulfonic acid. You don't have to draw it in full structure, you can just abbreviate it that way. Or you can use a different acid, it doesn't particularly matter that much. And then some kind of alcohol. The acid is catalytic. And then you get 2 groups on there. And this is our protecting group chemistry, so this is not reactive with Grignard's, as opposed to the ketone itself, which is reactive with Grignard's. 1D. This is a tautomerization question. So it just has, the only difference here is that it has a nitrogen compared to our enols. So to tautomerize, this is an amide. And does it specify acidic or basic? It specifies acidic conditions, resonance. Acidic conditions. So what would your first step mechanistically here be? We have an acid catalyst. Protonate what though?
Nitrogen.
The nitrogen, yeah. We'll protonate the nitrogen. You can do a resonance structure from there, and then deprotonate the oxygen. Okay, so it's still the same steps, even though we just have a different atom instead of carbon. 1E. Predict which of the following, or which of the compounds shown below will be more reactive with nucleophiles using a resonance structure-based ground state argument. The phrasing is a little bit strange there. Both of them have a resonance structure that looks pretty much the same, except one is a thioester. So our resonance and then here we can do the same. So which one is more reactive with nucleophiles, first of all?
The thioester?
Thioester. And they both have resonance, but what's the reason?
Is it because since oxygen is more electromagnetic than sulfur, that means sulfur is more happy having the positive charge than oxygen?
Maybe, well, if we use that as this being more happy having the plus charge, then this one is protected more because there's kind of, that would almost seem like there would be better resonance there.
Yeah.
There's something else, is that this has poor orbital overlap. So this is down period compared to oxygen, so it's a bigger orbital. So whenever it tries to form that bond there, there's worse orbital overlap. So that's the justification that I would write between the sulfur and the carbon compared to the oxygen and the carbon is different orbital overlap because there are different energy levels. F, oh, we're skipping F for now. G, increasing reactivity with nucleophiles. We probably gave you maybe like a more comprehensive list of these and kind of their order. Oh, sorry. Oh, good. I have your exam.
I don't want to see it.
Oh, I don't want to hold on to it.
All right, I'll take it. Oh, I gotta give you my promise.
Okay. Yeah, probably give you a more comprehensive list of yeah.
Is the poor orbital overlap, does that mean like the resonance structure is less? Or
Yes.
less relevant? Okay.
Yes. Less resonance contribution in this form. Okay. So ABCD ranking from least to most. The least reactive of these is the amide. The amide has pretty good resonance. They call peptide bonds the boring bond because they're not very reactive. Next to that would be an ester. Also has resonance. The difference in resonance also is partially because of the difference in electronegativity between nitrogen and oxygen. Or we're talking about liking the positive charge. Nitrogen's less electronegative than oxygen slightly. So that resonance structure is a little bit better. And then between an aldehyde and a ketone, an aldehyde has more steric hindrance, or sorry, a ketone has more steric hindrance, so it's going to be a little bit less reactive than an aldehyde. ECAD. So 1H is a specific example of a conjugate addition of a secondary amine. I did probably like the simplest one you could do. Does it say, oh, with an enone. Here's our enone. Try to, I guess the vocabulary is important, like enone, enolate, enol, different things that all start with ene that you might get mixed up. Conjugate addition, 1,4 addition. We're going to attack here. We'll get a minus charge up there, and then we'll protonate back. So secondary amine has two alkyl groups. It gets added on like that. Okay. You can have any secondary amine you want there. Even morpholine, I feel like that's still a secondary amine, so you could have that if you want, and that's an example that we talked about, so I'll make it a little more interesting. Okay. Right. That's it for page 1. So now some box problems. Did you do thionyl chloride on amides? Oh. Moving faster than I thought. Okay. So, thionyl chloride, or as I call it, Socyl 2.
Dr. Funk was wondering where we got the Socyl 2 thing from, and it was you.
But it wasn't me though that started it. Like everyone has been calling it Socyl 2. I feel like it's just been passed down.
I got it from Daniel, so whoever taught him that maybe.
Daniel?
Like the 210 LA that left last year.
My professor, my AP Chem teacher in high school said sophomore.
Really? I like Socyl. I think phosgene also works to do the same reaction, but that has a less appropriate name. So we will do, this is sort of like, you can think of it like a dehydration of an amide because we're losing H2O, we're losing the oxygen and the two hydrogens. Picture, maybe not as much for this one, but for other problems that you're counting your carbons. For some reason when that triple bond shows up, it becomes really easy to add or subtract a carbon somewhere. Okay, so B. Are you sure you can't do B? If you talk about LAH on nitriles.
We could
You can?
You could definitely do B.
Okay. Oops. For some reason, I feel like the mechanism for thionyl chloride, though, is something that we do in the next exam. Or did you go over the mechanism? Oh, you did? Okay. We can do that later then, after we throw everything else. Carboxylic acid. What is the oxidation number of that carbon? +3. And then we're using LAH. LAH is a 4 electron reducing agent, so we need to end up with what? +1. -1, correct. That is going to be an alcohol. Okay. C. We are ending up with a cyanide on the end. You can notice that it's, if you take the cyanide group, it's attached to the beta carbon, and that's a pretty good indicator that you're going to be doing some kind of conjugate addition. So on the enone, we have the alkene here that gets attacked. I heard someone mention catalytic sodium cyanide. It's catalytic, not most of the catalysts that things that we've been calling catalysts have been like to protonate or deprotonate to start, and then you end with the same asterbase at the end. Here, when you attack with sodium cyanide, I'll just draw off mechanism. You have your enolate, now you have the cyanide on there, and you'll regenerate another cyanide by deprotonating HCN. And so now you can kind of see the, at least mechanistically, where tautomization and conjugate addition overlap in this intermediate step of going from your enolate and then protonating back to a ketone. Okay. Do you know how to do 2D? 'Cause so far, everything except for the ester we haven't known how to do. 2D. Acid chlorides and amines. Okay.
So for you, I have no clue.
We'll bypass that for now.
Crazy. We got so
For E, shift places here, double blocks as well. And this one, it looks complicated, but just don't overthink it. So this is a real big withdrawer of that nitrogen. And water is byproduct. How we make these are starting from everything down here that was the original carbonyl, and then everything above is your, I guess, hydrazine derivative. I'm not exactly sure what we would call this one. And if you don't put it in the box, we won't count it. Obviously, not.
Can we just put TS to substitute hydrazine, or do you want the full?
That's tosylate. So not.
Is it not? Oops, my bad.
Tosylate looks big.
It's basically the same thing.
Pretty much. They're both pretty withdrawing, so.
I really see it different.
Okay, so that's 1E. We're kind of flying, I feel like. Whoa.
This one isn't too terrible.
Okay. I guess we still have a whole problem set to go over there, so we'll just do that. Two different ways isobutyric acid could be prepared in one step, starting with a nitrile or with a Grignard. Did you do the nitrile hydration mechanism yet?
Nitrile hydration.
That's long. I forget how many steps it
You
is.
have to show me.
Pretty lengthy.
Which one is this?
3A.
3A? Oh, the one with cyanide, with H2O and H3O?
So Grignard and a nitrile. Whenever you do of a nitrile, you get a carboxylic acid. So all of the carbons here are going to be the carbons of the nitrile, and then the two oxygens and the hydrogen are going to come from the hydration. So again, make sure that you're actually counting your carbons, because it's easy to miscount whenever triple bonds get there. I don't know, it's some weird psychological thing. So that's our nitrile, and then acid catalyzed hydration. Okay. And then to make carboxylic acids from Grignards, we're going to use carbon dioxide and then quench with acid. And here, you're going to use only these three carbons as part of your Grignard. So you have isopropyl Grignard. So you put the Grignard reagent in the box, and then make sure that you put the semicolon quenched with the acid in the box over the arrow. It doesn't make sense to put Grignard in the acid and then react it with that. Okay. All right. two different enones to make 2,3-diethyl cyclopentane 1-one. Is this not the right? I might be using an old exam.
No, it's no, we're
Oh.
just saying thing.
Okay, two enones. We're going to be doing conjugate addition here. Does it specify anything else? Oh, cuprates. So we're going to be doing conjugate addition. You want to look at places where the alkyl groups are attached to figure out what kind of cuprate you're going to use and where you want the alkene to be. We have these two ethyl groups in these two positions, but the question is, for conjugate addition, which carbon do you attack the cuprate with, or attack with the cuprate? So this is alpha.
Beta.
I was wrong, yeah, beta. Beta. Because it's 1,4. If you count 4, from the one you attack, it's 4 to the oxygen, so 1, 2, 3, 4. Because that's where the minus charge ends up. So, oh, adios. I won't. So we gotta find what beta carbons have alkyl chains on them. First, we have this one. I think this is the more obvious one. And we're gonna use diethyl cuprate. We got a bunch of cuprates as well. So that'll give you that. We can't just use another ethyl cuprate and do it on this carbon. Even if you have the same enone here, that wouldn't add to that position. So this is the beta carbon that we want to add to. So we're going to add on this methyl group. Using dimethyl cuprate. My semicolons are getting weird. Okay. That's the tricky part of this question, is the exocyclic alkene, because a lot of the other examples, like whenever we draw them out, or like draw out a mechanism, it's going to have the alkene in the ring that you'll do the conjugate addition onto. Here, it's exocyclic, but it still works because it's beta. Does that make sense? Maybe just once you see it, you're kind of like, oh, yeah. All right. Another double box. Another double box. Okay. You did do green yards on nitrile? I feel like I'm behind. I feel like you guys are flying through this stuff now. This is great.
I think he's locked in because he's separated from like the snow day that happens.
Really annoyed about this snow day.
Yeah, that's so neat to kind of mess everything up. This is exciting though. I can make more interesting syntheses. Because all of last semester and like the beginning of this semester, I was like, oh, you guys don't know that yet. Come on, you know. But now you know things. So
We actually don't know anything, so the easier syntheses we do better.
We know so much. I can almost see
okay. Two different nitriles. Whenever you use, whoa, thanks. Whenever you use nitrile, or oh, I guess it does it specify Grignards? No. How do you make ketones from nitriles? This with Grignards. The carbon that was the carbon of the nitrile is the carbonyl carbon. So all of the two alkyl groups on the other sides are going to be the Grignards that you use, and then everything else will be the nitrile. So here on the left side, this is going to be, so you see this structure here, this is going to be our nitrile, and then we're going to use these other two carbons, so an ethyl Grignard, and then quench. Okay. And then from the other side, we have 3 carbons in the nitrile, and then we're going to use an isopropyl granurate again. We use over there. Quench. Yeah.
If we have time, can we go over that mechanism?
It's a pretty, I mean, I can do the first step. It's a pretty long mechanism. I think on my YouTube channel, plug that. I think I have the full thing.
How much money have you made on your YouTube channel?
$0. Because I have like 8 videos on there from like 2 years ago.
You gotta start getting sponsorships.
Yeah. I want to start making more videos because I enjoyed it as college happened. I didn't have time. So there's our ethyl granure attacks. We get that. Then we add our acid. We have an imine, and then the next part is just, that's the long part, is the imine hydration back to a ketone. But the first part of it, getting to the imine, that's the more relevant part of the mechanism, I guess. Okay. That's that one. So we're good with the double boxes. Any other questions? Mechanisms? Um, Which- what was it, the steps of the thing?
It was just, yeah, but it's okay. It's in minutes anyway.
Okay. It's just, it's this, but with a minus charge on the nitrogen.
Okay.
And then you protonate the acid. These mechanisms are getting longer, but they're, I guess, more logical between the steps than the ones from last semester. Before you have that framework, they kind of seem maybe random sometimes. So here we have a cyclic hemiacetal, and we're going to, or hemiacetal, and we're going to the full acetal. Assuming this is what it says. Is that what it has? Okay. So our first step here, we want to, well, just looking from starting to ending, we're changing this OH to a methoxy. So we want to get rid of this somehow. We're going to do that by protonating it, which will make it a water group, which is a good leading group. And all of these steps are equilibrium back and forth. You don't need to show the bidirectional arrow. So now we have our water group on there. Are you guys able to see over here? I realize there's a lot of like things blocked. Okay. So we're going to use one of these lone pairs on the oxygen to kick off water. Okay. Now this is pretty electrophilic here on this carbon, so we're going to attack with a methanol. And now we're going to regenerate our catalyst and get the product, excuse me, by deprotonating with ethanol. Cool. So this is the ending of Wolff-Kishner. Just like from last semester, like we didn't put ever like a full acetylene zipper or a full ozonolysis. They're just long. But here, the important part, so we have a base, we're in basic conditions. Our first step is going to be to deprotonate. The most acidic proton are the ones here on this part of hydrazine, or what was hydrazine. Deprotonate, get a minus charge on the nitrogen. And then we can draw our resonance structure. And you can do these two in one step, really, if you wanted to. You can just show the other resonance structure instead. We have a carbon anion. This will then get protonated, because carbon doesn't want to have a minus charge. And make sure that you don't make a dianion here, because that's the next step, so you might get mixed up. Do I deprotonate here first or protonate there? Protonate there first. Now we can deprotonate this second H. The byproduct is given as nitrogen gas, so we want to get a triple bond there. I'll show it this time in one step. Like not show the resonance structure. We have a cyclohexyl anion that we will protonate with water. To get cyclohexane. So we have methods to go back to. Okay, we have methods to go back to alkanes. I guess we had some previously as well, but letter C. This is the first part of nitrile hydration. What does this, if you were to keep going, where would this go? We're going to end on an amide. What is that where it actually would end? Yeah, we'll go with carboxylic. Oh, this is basic condition, sorry. Okay, so hydroxides are catalysts. So we're going to start by using the hydroxide. We don't really have any acidic protons on here though, right? So we're going to use the hydroxide as a nucleophile. Okay. We have a minus charge of the nitrogen. Before we do anything else, you're going to protonate that with water. that look familiar to anyone? What's that?
We just saw that.
Yeah, that was the tautomer question on 1D or something. Now we're just going to tautomerize. This time in basic conditions. Was it basic on the front or was it acidic? So you can do it either way. Basic, we just protonated here, so chances are we're not going to want to deprotonate there immediately again. We'll just take this right back. Which will happen, you'll get reversible, but we're going to deprotonate to OH. Again, you can draw the resonance structure simultaneously if you want, and just push another arrow. Here, though, here's our resonance to get the minus charge on the nitrogen. Now running out of room. Whoop. And then we'll protonate and get our water or hydroxide back. Oh, yeah. Okay. So LEH. This is going to take us to alcohol. What's up? You guys have a question? No. Okay. LEH is a hydride donor. We're going to donate a hydride with the carbonyl. This is our tetrahedral intermediate. This is H on there. You'll then take out a chloride. Get to an aldehyde as our intermediate. And then we'll show another hydride coming in, attacking the carbonyl again. Two H donors, don't worry about those. And then protonate with water in the workup. So 2 hydride donations. Okay. Questions on any of the mechanisms? Okay, syntheses. Starting with an enone methyl vinyl ketone. And OH. So a couple different things happened here. We extended the chain on the left side. We also went from a ketone to a tertiary alcohol. Excuse me, so that tertiary alcohol is hinting to me that we're going to use a Grignard and ketone at some point. And I also included into the fact that we're going to use that Grignard last, because if we do that first, we get an alcohol. We no longer have an eno, and we can no longer do conjugate addition. So you need that carbonyl to be there to do conjugate additions. So that'll be our last step. On that ketone. And then we can't do conjugate additions with Grignards because that would attack the carbonyl. So what's our softer nucleophile that we do alkyl conjugate additions? Cuprates. So we're adding on just the phenyl. And quench. Good enough? Okay. Letter B. We have so differences here. We have one extra carbon that we need to add on somehow. Bromine's gone. We have an amine. So this is organic one reaction. A way to add on a carbon and nitrogen simultaneously is with our friendly SN2 acidic cyanide. I almost drew a pen. I'm tired of seeing alkynes that look like that. They aren't like that.
Do you detect points every
Draw
draw
them
like that?
straight. What?
Do you detect points every draw like that?
I don't think I've deducted points, but I should start.
No, that'd be pretty bad.
The problem is that like deducting points with something that's just drawn a little bit weirdly is like
Gets into weird territory.
it gets into weird territory because it's not like wrong. Like yeah, maybe the molecule is just like has a little crick in its neck and it's just like bent for a second, or you know their molecules are moving, and also
They wait.
if like someone has like a crazy answer that's just like wrong, then that's where you take off points versus if it's like just drawn a little weirdly. And for a question that's only worth like 2 points, it's like anyways, my rant's over. 4 electron reduction of nitrile. LAH. You can use the test to take the test. There's a couple of places on here where that's the case. We're going to skip over C. There's a few different ways to do C, and I was like, oh, you already learned Fisher certification, but you didn't. So,
Is that a same energy?
what's that?
I feel like it's possible now.
I don't. Based on what you said for the other problem, I don't think it's possible yet. But I'll let you think about it for the next few days. So letter D.
I said.
I still have.
Okay, we're going from An alkene, we're getting a carboxylic acid on there. That's styrene over on the left. In terms of carbons that are added, we added on one carbon here. Adding on a carbon that's a carboxylic acid, that kind of hints to me that we're going to have a Grignard on what?
CO2?
CO2, yeah. So our Grignard is going to be everything else down below there. And then how do we make that Grignard in 2 steps? Yeah, HBr, hydrogenation to give. See, this is basically Orgo 1, you know?
I don't think we learned that.
You didn't learn hydrogenation in Orgo 1.
I don't remember it.
Hold on.
Was it?
Yeah.
Yes. In the regular. I remember specifically drawing out the first 4 elements of the periodic table. Day 1.
Oh, we didn't do that.
Maybe not literally day 1. Also, we did do that. We wrote out that it was organic chemistry is a language. Like,
Yeah.
Letters are the elements.
We had the same talk.
Or words are molecules. Sentences are mechanisms, and syntheses are paragraphs.
Yeah.
Organic chemistry is basically math. Like it's logic. It's just not math in like a calculus sense, but it's they're logic. They're logic puzzles. A mechanism is a proof. It's like the same thing.
I'm way better at that.
Let's go over the problems.
Oh yeah, we're going over the problem set. Just write it out because I guess I have all of yours, and if I don't have all of yours, then I'm. So that was that. Okay, switching gears. Were mechanisms or syntheses first? I just wrote them on the back of my phone.
I like mechanisms.
Synthesis was first?
Hey Jay,
Yeah.
I just reminded, you can check the file, but I have a second copy of it as well. Did I use that?
For what? I mean, like.
I think I was supposed to give it to Aiden and I forgot.
No, you have my copy.
Oh, a second physical copy of the packet?
Yeah,
Yeah, I mean, why would I have a problem with that?
I want you to make sure that.
Maybe you could turn it in again. So there's
You can tell because the first page is like.
I don't even have a copy of it. I had the thing, and I just wrote it out. Okay. So, did we think that these were hard?
There's like 2. There was 2 questions. The other ones are pretty fun.
Okay. So, except for, well, I don't know. In general, these are a little bit more difficult than I would expect on an exam. Maybe take a little bit more time to think through. There's 2 different ways to do this, or at least, I mean, there's a bunch of different ways to do all of these. But I heard from whenever I was helping people 2 different ways to go in the same, getting the same thing. The first would be to do an elimination with t-butoxide. It's bulky, it's not really going to interact with the ketone or do anything weird there.
My king.
What?
I was saying T-butyl, my king.
Yeah.
He carried me last year. It was great.
Okay, so now we have an enone. What did you say? Oh. We have an enone. We want to add something onto the enone. And I would be careful with what you do for conjugate additions. In terms of like functional group, that's your goal. In terms of functional group compatibility, sometimes people like put random things on a cuprate and it's like, well, that's not gonna work. So I would just stick to play it safe because you're not gonna need to do anything else. Just always stick to just alkyl groups on here. So here I'm gonna add on everything on this side except with not having the oxygen there. So
If we put the oxygen, would it be wrong?
yeah, I think so. Although I don't think you can have ketones on a cuprate. If you looked it up and it said you could.
I had a LA for the normal chem section that I know. She looked up. She said, yeah.
I would stick to just alkenes or alkanes or
On
something.
the problem set specifically, if we did it with that, will we lose points? It's kind of.
Oh wait, you guys still have to draw a problem. We'll do that after this, and we'll see which one gets selected.
Oh, yeah.
Like you have to you're gonna not choose. We're gonna do like a random number for which one gets selected.
Oh.
Just don't
Yeah.
pick that one.
I did it in a different way, where,
There is a different way. I'm gonna do the second way.
It's the yellow.
Cuprate, quench. Someone looking up to confirm if carbonyls on cuprates are.
I couldn't find anything. I was looking, that's why I did it a different way.
Yeah.
Because I was like, I don't feel like I would have that. Because it just says alkyl groups, but then it's like, we're leaving it purpose in the videos. But
Yeah.
that's what like Wikipedia says in the textbook.
I haven't seen anything with carbonyls on cuprates either. But then to get from this alkene to this ketone, you ozonize. Okay. Cool. I guess I'll just draw out the alternative way that I did separately. This one's a little bit convoluted because of protecting group chemistry. Because anytime you have a protecting group, that automatically adds 2 extra steps. You have a protection and then a deprotection. But I was like, I don't know. So I first did a protecting of the carbonyl. I wanted to make a cyclic ketal.
Would we be marked off if we didn't put the puzzle thing? I didn't,
You can just use acid. It doesn't matter.
but if I didn't put any, because I didn't know.
What do you mean?
I just put the diol.
Oh, with no acid?
Yeah.
I'll put H plus next to it. I don't really, it's not that big of a deal. Halides, most of the time when we write Grignards we use MGBR, but you can also use Grignards with chlorides. Everything with chlorides. Okay. And then we want to add on these 3 carbons. So do it in the form of an aldehyde so it can attack it. But the problem with that is that will turn it into an alcohol. And then here, I'm going to be a little bit of a cheat. I'm going to, because I mean it will work, that if you do, whenever you do the quench with acid, just add a little bit more acid in there, and then it deprotects the ketone. Okay. And then PCC. So this one is longer, but that's what I did. Yeah.
If we did protect it before adding the magnesium, would it just remove the oxygen? Or what's the
So if it didn't, so if you have a Grignard here, it's going to be too small to make like an internal ring, but it will react with one of itself. Like it'll go attack a different carbonyl elsewhere in the solution. So you do have to protect it. Okay. So that's that one. Second synthesis. You say hold on. Oh. Okay. There's like a trend here. I feel like we've done this reaction like 3 times or 4 times today. We want to get a carboxylic acid. It's kind of suspicious that it's on the most substituted carbon. You're like, why? How's it getting there? We're going to, in the last step, use CO2 and acid, well, acid quench, from a Grignard to get our carboxylic acid. Bless you.
Thank you.
How we get this is by adding magnesium to that alkyl bromide. Well, okay.
It's the only thing I know.
NBS, you can do NBS. It's slower though. NBS is so you generate bromine, radical bromine, like in situ, slowly, so that it doesn't. You tell me, what does NBS prevent?
I don't know what it means.
So you use NBS whenever you have an alkene that you don't want to react with.
Right.
So it does it like an allylic bromination. So here I just use bromine and light.
That was the first reaction.
This was there's zero shot this was the first reaction you learned in organic.
Yeah.
You started with radical bromination.
Yeah, right after he talked about the types of reactions.
H-nu.
H-nu.
Represent. That's
If
my,
I
that's
still
my
had-
fraternity.
If I still
I'm an
had this
H-nu.
from last year, I could show you. I had funk.
Oh, maybe you're talking about like the first day he like just gave an overview of what you'll learn or something.
Huh?
Like maybe he gave like an overview of what you'll learn. But
That was a year ago. I don't remember this.
there's no way he like.
This is ancient
I
times.
have them.
Okay. Last. How many syntheses? Oh, that was number 2. Are we good on synthesis number 2? Okay. Acetaldehyde to getting this. Okay. So that amine is attached sort of suspiciously again to the beta carbon. So that's hinting to me that we're going to do a conjugate addition on an enone. Do we see that? Or is that maybe not as, just I guess immediately obvious? Look, for syntheses, definitely look at, if you have something that's kind of seems out of place and random and is definitely not in the starting material, look at where it is relative to the carbonyl. Here it's on the beta carbon. That hints to me that it's going to be conjugate addition. We're going to end with that. I'm confident we can make it otherwise. From this enone. And then how do we make this aldehyde from this, or how do we make this enone from this aldehyde? We have to add on 2 carbons. Yeah, Grignard, and then I use PCC. Jones is more toxic to the environment, so I'm sorry that you hate fish,
I
Sam.
meant to say pieces.
So using a Grignard on an aldehyde or ketone gets you an alcohol, so you have to oxidize with PCC or Jones. I mean, it wouldn't be marked wrong, but yeah. It's the chromate. Yeah, there's that one. Oh, I was like, we're flying through this. We have 12 minutes left. 12 minutes. Okay. Class synthesis. Oh, I bet this one gave you
My
some
favorite.
good
This
times.
is actually, I got it first try of synthesis.
So,
Yeah, that is.
Different reagents. Like,
is that the right number of carbons? At this point, it doesn't really matter.
there's 10 carbons.
1, 2, 3, 4, 5, 6, 7, 8. No. 1, 2, 3, 4, 5, 6, 7, 8, 9.
It doesn't matter.
It matters
I only
to
drew
me.
like 2 carbons, so.
Yeah. Can we just draw it as a circle? With a
Several equals.
Low key, I saw that on one of the 2 times. It was really funny.
It's 23, 1, 2. Okay, cool. So this one, obviously this is a challenge problem. One like this wouldn't be on the exam, but I hope that what your solution to solving this one was to look through your notes and see everywhere an alkyne shows up and be like, how is this alkyne getting there? I remember, I feel like I might have had this problem whenever I took the class, and I was thinking like, oh, you ozonize, and then you like find some way to like
That's what I
reduce the carbonyls, and then do you like
And protect it.
tetraphenyl or triphenylphosphine and carbon tetrabromide turns into bromines or double elimination, something. No. No. But I hope that you went on that adventure of the mind.
There was no way to change which carbon.
The answer to this one is Eschenmacher fragmentation. So we have to make this into we have to add everything to make it fit for that. So we have to turn it into a tosyl hydrazone, and we have to have an epoxide there. Unfortunately, as just to throw another rock in your bike tire, you can't use MCPBA here to make an epoxide.
What? You can't?
You cannot use MCPBA to make an epoxide here because this is a very electron deficient alkene. Because what is a ketone in terms of donating, withdrawing? The electron density withdrawn from that alkene, and so you can't use MCPBA because you need those high electrons in the alkene to attack or to grab the oxygen from the peroxide in the MCPBA or whatever parasitic acid, whatever
That's
you
crazy.
What do you use?
So you use the test to take the test, and you look at mechanism D or something, whatever it was. The one uses sodium hydroxide and peroxide, and that's how you get the epoxide on. So you do a nucleophilic addition of the peroxide to get the epoxide on there.
I did that, but I forgot to put the catalyst.
Did you just put peroxide, or would you put?
No, I did that, I just didn't put the cap.
Oh, yeah, that's fine. That's, semantic. Okay. So the next step here is to add tosyl hydrogen. You know what, I'm just going to abbreviate it as same thing. Get rid of that. And then you can do this in acidic conditions, base conditions, or just in the presence of heat that will fragment. Triethylamine is pretty common. I think you said yesterday in office hours you use pyridine as the base. I think the mechanism you probably did in basic conditions, so that's what you want to do. Yeah. Yeah, I think it should be fine. Okay. So that was all the species, right? So now we're on to the mechanisms. Okay, we have this two bromines. Two hydroxides, water, and we're making an aldehyde. Okay. So you could deprotonate, I guess. That I don't know exactly what the pK of that proton is. It's probably like not super high, so you could maybe conceivably deprotonate a little bit of it. But here, hydroxide is going to be better as a nucleophile to do an SN2. This is, first of all, a really electrophilic carbon because of those two bromines, and it's next to the benzene, so there's a little bit of withdrawing there. And there's no competing elimination. You can't do an E2 in any way here. So hydroxide attacks, kicks off the bromine. That's our SN2. Then with the second equivalent of hydroxide, we can deprotonate this oxygen. And kick out bromine. This is not, the mechanism doesn't really look similar. I think it's just reminding me of it because there's several halides on here and we're doing like some kick out things. There's a reaction that I really enjoy later in the semester called the iodoform reaction, and that one's fun. And it's kind of feeling like this. I think that one's like 3 equivalents of hydroxide, or maybe 4 equivalents of hydroxide, 3 of iodine, something like that. I don't remember exactly. I'll have to look at it, but that was fun. Okay, good on that mechanism. I think it's 4 of hydroxide and 3 of iodine. So this one, and I want to note just now, because we're starting the one, well, this one has an oxygen nucleophile, or does a conjugate addition with oxygen, and so does the last one. Conjugate additions happen because of softer nucleophiles, and in these cases, they turn out to be softer. Most of the time, though, oxygen nucleophiles would rather go straight for the carbonyl if they can. Catalytic T-butoxide, also kind of misleading because that feels like an E2 reagent, but it's a base. So. Okay. I'm going to draw a big arrow. No, I'm not. It's like a nerf. Basic conditions, we have a basic catalyst. This will deprotonate the OH. Then we're going to use this as a nucleophile on the benzaldehyde. Did you have a question? Great. Just abbreviated the benzene as pH. make this enone a little bit more clear. Then we have that is in the spot to do conjugate addition on the enone. And then to regenerate our catalyst and also get the product, we will protonate the enolate with T-butoxide, or T-butyl alcohol. Yeah.
Why do we have both of them, those two stereogenic centers pointing the same way?
I was hoping that I wouldn't get asked that question because, to be honest, I'm actually not sure of this reason for the stereochemistry here. Probably some secondary orbital overlap. But yeah, that's a better question for fun. I haven't read up on this reaction or why it has that stereochemical consequence, but yeah, I apologize, I'm not sure. Okay. So this next one is a spin on the Shapiro reaction, which maybe you talked about in class. You did?
We did.
Okay.
Sadly.
That's used on causal hydrozones of aldehydes or ketones to make vinylic anions. Hard to write and talk at the same time. 2-methyl lithium. Here we're making alene though. Alenes are fun. Okay. Did I draw that all right? I think it's okay. And then the byproducts. Okay. So methyl lithium, that's a very strong base. So where is our most acidic proton? Here. There's nitrogen. Okay. And then we're actually going to do 2 protonations here. So we're going to make a dianion, which is what's a little bit strange about this reaction. But it doesn't really matter because we're working with methyl lithium, so it's just going to pull off protons wherever it sees fit. In terms of where they're most acidic, the next most acidic one is the one right here. There is no proton there. Go figure that. So deprotonate there, and then you can push arrows up to make your first alkene so that you can avoid just in your intermediate having a carbon ion. Makes it a little nicer. You keep everything. You keep it as a single anion. What's that?
No.
Oh, and kick out your tosylate. That's where your minus charge is going. I was like, charge needs to be conserved here. So do your second deprotonation, form an alkene, push this up for resonance for a double bond between the nitrogens, kick out the tosylate. That way, again, you keep just a single minus charge here. So we have an alkene now, and minus. Okay. And now with our minus charge, we're going to shoot our arrows backwards to kick out this oxygen or kick off this oxygen, form our second alkene. And then we're still going to have the minus charge, but now it will be on the oxygen. So minus. And then we will protonate not with methane, but with water.
You get it wrong if you protonated with methane.
Yes, I would definitely take points for that. This is not catalytic methyl lithium. That'd be kind of crazy. Yeah.
If I did that right, the steps, except the arrows are wrong on the third one,
This one?
but I did it like that, but it's still done.
You did it like this, but the errors are wrong?
Yeah, like I did the same step, like I got the same,
You got to this intermediate,
and then I got to the.
and you got to that, but you just pushed the errors a little wrong.
Yeah.
The synthesis and the mechanism are both worth 2 points, so if it's not like a crazy error, then I'll give you the point, you know. Because there's like several, I'll see. Well, you know what, we'll see. we still haven't chosen them, so this one might not be selected.
Well, you usually get something.
Huh?
No. I just did something like
Well, that was probably fine. Okay, last question. We have going from an enone. This was your hint for the Eschenmacher, kind of thinly veiled hint. Okay. So we're going to use the hydroxide not to deprotonate anything on the enone, but to deprotonate the peroxide, which has a pK of, what did you say? I'm not sure what you said. You sounded like you were close to it, but I don't know. What was the number? Oh, no. Sorry. I think it's 12, but I was like, yeah, it's pretty close. It was like 11.8. So. So here we have our OH. This is a softer nucleophile. So it will do conjugate addition onto the enone. We'll make our enolate. And then, wait, Bayer-Villiger is this semester, right? Okay. Does Bayer-Villiger sound, I'm guessing it's later this semester, never mind. What other, I guess epoxidation, the mechanism is somewhat similar. We're going to push the arrow down to make the carbonyl, use the pi electrons here to form the epoxide ring, and then kick out our hydroxide, which regenerates the catalyst. And that's the problem set. Okay, so we have 4 mechanisms and 4 syntheses. So we're going to have Siri choose a number 1 to 4.
Can we vote on that?
Can we go in?
I don't think you can vote. I don't feel like that's.
There's a correct.
I don't have a D4.
You don't have a D4.
Not on you.
No, I don't.
Draw.
Not on me.
Draw 4 things, and then we pick one of the things, but you assign a different number.
Okay, I have.
Just ask Siri.
I have. Okay.
Just ask me.
Pick a random number 1 to 4.
I got that one.
Pick a random number 1 to 4. Oh my gosh. Pick a random number 1 to 4. So, synthesis 2.
Future of AI, by the way.
Pick a random number 1 to 4. And then mechanism 1. Oh, that's light. I feel like you would have voted on that anyways.
What was mechanism one?
That was the SS2. Okay.
Thank you.
Bye everyone.
I was really concerned.